Okay, welcome back everyone, and we're looking at the public use mock external exam or public sample from 2020 released by QCAA for specialist mathematics, and we're going to look at the questions from 6 through to 10 on the paper 1 tech-free exam. Okay, so this is the tech-free paper 1. You might want to catch my corresponding video if you haven't already caught it for questions 1 through to 5, the first 5 multi-choice. So let's go through some solutions to these ones. In question 6, a slope field that represents the differential equation dy dx equals x over 2y is, and we have a choice of 4 there. Now we know dy dx describes the slope or the gradient, and we look at the given expression x over 2y. We need to understand that both x and y have some effect on the slope field as we scan across up and down, left and right. There's different types. Some only depend on x, some only depend on y, and some depend on both. And this one depends on both. So as we move along x, things will happen to the gradient, and as we move along the y-axis, certain things will happen to the gradient too. And we also need to consider both positive and negative. Now just looking at the numerator with x, so as x increases, in other words, as we move along the x-axis to the right, in the positives, for example, the value of dy dx will increase because we have x on the numerator. Whereas if we have y increasing, especially if we're looking at positive values of y, the overall value in the positives of dy dx will decrease because it's on the numerator. And it may be interesting that it's a ratio of 1:2 because we have 1x over 2y. And we can have various combinations of positives and negatives. We could have x and y both as positives, and we'll get a positive gradient. We can have both negative x values and y values, and we'll get a positive gradient again. If we have one of them, either x or y negative, we'll have negative gradients. So we need to be all analytical about this. Probably the last thing helps us a great deal when we look at the 4 options, but we'll have a look at also the nature of how, especially starting in the positives, how I originally said if x is increasing and y is increasing in the positives, what's going on. Alright, so if x is increasing in the positive part of x-axis, which is quadrant 1 here, we can see that on the diagram, we should have an increasing, if we don't go anywhere in the y direction, we should have an increasing gradient. Now in the first one we don't. As we go across any value of x, it appears the gradient is unchanged, and that definitely seems to be the case wherever we go, and into the negatives it's the same too. So x is not affecting it. We're not getting the pattern either of when the signs of x and y are the same. We're not getting the positive gradient there. Like for example, in quadrant 1, x and y are both positive, yet we've got negative gradients. There's probably other reasons why that one is unsuitable. A's out. B, we can see that when x and y are positive, so in the first quadrant here, this region here, we should have, again, positive gradients, but we don't. We have negative gradients, and there might be other reasons why B is out, but one reason is sufficient. Now, that continuing in that first quadrant test that I'm using, we do have positive gradients there as x and y are both positive. If x and y are both negative, we're talking about this quadrant down here, quadrant 3. Okay, and we should have positive gradients, but we don't. We have negative gradients there that we have falling. So that's out, and there's probably other reasons for it, which leaves D, but let's check it out. Alright, we have x and y positive in the first quadrant here. We have positive gradients. Yep, we have x and y both negative, so we have positive gradients in the third quadrant. Good. We have x negative in the second quadrant and y positive, and that means we have a negative gradient overall. Yes, that seems to be valid. And likewise, we have positive x but negative y in the fourth quadrant here. And so we have negative there too. And there's other reasons just quickly too. As we increase x, the gradient of, as we go across here, for example, look at the first quadrant, for example, the gradients are increasing. Also, as we go up here, the gradients are increasing if we go vertically up from any x point. So, sorry, down, I should say, because the y, you remember, is on the denominator, sorry, so it's decreasing. And I said that originally in that question. Question 7 is, which is of the following best describes an interval estimate of a population parameter? And we've got 4 choices here. Now the answer is D. It's an interval that is likely to include the unknown value of the population parameter that we're looking for. Okay, so we find it's the best answer as it describes an interval that the population parameter we are interested in might lie in. So that links to D pretty well. The main example in specialist maths is that of the confidence interval for the population mean. And also the parameter is unknown. Alright, largely speaking, the parameter is unknown when we're dealing with this stuff. So there's 2 good reasons there. An interval estimate does not directly talk about uncertainty, so that's certainly not the best description there. Okay, and C, I'm skipping B for a second, but so if we're using an interval that is calculated using the population parameter, but we don't know it, so how can we use the population parameter in the calculation? So that's not valid. Okay. B, the proportion of values expected to lie within an interval. Well, that kind of sounds like it's feasible, but an interval estimate is not really about the population, the proportion of values expected to lie within an interval. Okay, it's more akin to, an interval estimate is more akin to us expecting that a certain percentage of samples taken in a certain way using a constant sampling technique would contain the population parameter, and we tend to use mu, the mean. So it's certainly not the best answer there. So it's not our answer that we want. We want D. Okay, in question 8 we've got Argand diagrams and a complex number scenario here. So we're given that Z equals A plus BI, and we're told that A is negative and B is positive. So the Argand plane that represents a possible position of W, another complex number. Now W is the conjugate of Z times I, alright, with the operator I on the front there. So let's find Z conjugate first. Z conjugate is A take BI, and we got I times Z conjugate, which is AI or IA times BI times I, which is I squared. Alright, and now we've got AI. Now I squared is -1 plus B, or we could write that as B plus AI, which is interesting. Now we're told that A is negative and B is positive. Alright, so we go in the positive direction for our real Z, and in the imaginary Z direction we go down. So we're going to the right and down for W. If we look at option C down here, going to the right and down on the Argand plane, that's talking about this quadrant here. So C is the answer. Question 9, an antiderivative, looks a bit daunting, even though elements of it might look familiar with our work we've done on antiderivatives and integration, plus what we see on the QCAA formula sheet. So what we can do is actually use one thing we can do is use a different technique and basically look at the options, and if that's too daunting, we can look at the options and use the derivative to reverse the process and see if we can get the antiderivative expression at the top, the expression we want to take the antiderivative of, excuse me. In a multiple choice scenario where we want to get the questions done. Now this mock has 70 marks on it, so if I remember the calculation, that's less than 1.3 minutes per question, so hopefully it doesn't take too long to use this procedure. Okay, that is an average figure too, and it does depend on how many marks are put on the exam. This one has quite a few marks, it has 70 in 90 minutes. Alright, let me know if I've got that calculation wrong, but I think I can remember that as about 1.28 or 1.3 minutes per mark. Okay, this is worth 1 mark. So let's see if we can reverse these answers to get our expression up the top, and by that we need to use the derivative. So I'm going to start with option A first up, and if we call that y, just to give it a name, so it has some sort of identity, it doesn't go through an identity crisis, and we don't want that for our mathematics. If we've got this here, well, we could use the chain rule on this, and look, the constant's going to disappear. It'll become 0. In other words, when you take derivative of that part. So we basically got. Let's introduce the variable u. Let u equal the inner function there, arc cos of x over 2. Okay, and from our formula sheet, we can fairly easily calculate du dx. So using our QCA formula sheet, we know that the derivative of arc cos x over 2 will be negative 1 over 4 take x squared. And once we've made that u substitution, y equals negative log of u. So the dy du expression would be negative 1 on u. So with our chain rule, we have to multiply these two results together. So dy du times du dx would be negative 1 on u by negative 1 over 4 take x squared. And we basically have a positive, we unsubstitute the u, so that was inverse cos x on 2. So we have both of these terms on the denominator. I'm deliberately writing this one first because I can see a match up there in part A, and that's a relief because it was the first one we had to try. So from a time utilization point of view, that's good. Okay, so A worked out. Last one. Question 10, we've got some definite integration here, and again the QCA formula sheet is very helpful because if we're looking at the integral of some parameter a over a squared plus x squared dx, we know that it is arctan x on a plus c. Alright, and that fits because it'd be like saying a is 4, alright, and therefore a squared is 16, alright. If a is 4, then we can say a squared is 16, and we have to remember to look at the terminals too because it is definite integration. So we're looking at inverse tan, alright, so for this expression here, x squared over x squared plus 16 on the bottom, and we've got arctan x over 4. Now it's definite integration, so we put our terminals in, limits there, and compute the values once we've got the expression sorted. So we have inverse tan of a half minus inverse tan of 0. Inverse tan of 0 is 0. We can express our exact answer as arctan 1/2, and that's option B. So we've now completed the 10 multiple choice questions from the public use mock from 2020.